Welcome to this explainer. Today we're doing something really exciting. We are descending straight into the matrix of vector databases to trace the exact journey of a query. We aren't just looking at the surface-level magic of large language models here. Oh no, we're going deep into the plumbing to expose the silent failures of enterprise Retrieval-Augmented Generation, or RAG. If you've ever found yourself wondering why your incredibly advanced LLM is confidently hallucinating even when it has full access to your entire corporate knowledge base, well, you are definitely in the right place.
So here's our structural map for today. We'll kick things off with the evolution of RAG, dive into vector math and silent failures, untangle the metadata filtering dilemma, look at score fusion and re-ranking, and finally wrap up with conquering the context window. Let's jump right in.
Part 1. The evolution of RAG.
It's honestly crazy how fast this space has moved. We started out with basic vanilla RAG. Embed a query, do a quick lookup, and just dump the text chunks into the LLM. It was fast, sure, but super vulnerable to ambiguous phrasing. Then, that evolved into advanced RAG, where we started using query transformations, like hide to dream up hypothetical answers and multi-stage re-ranking pipelines. And today, the state-of-the-art is fully autonomous agentic RAG, where LLMs are actually managing complex routing across multiple different indexes and even evaluating their own retrieval progress.
Now, what's fascinating here is how the latency profile totally flips depending on your enterprise workload. Vanilla RAG gives you those blazing fast, sub-50 millisecond speeds, but your resilience to errors is basically zero. On the flip side, agentic and graph RAG offer amazing error resilience and the ability to connect completely disjointed sources. But you're trading away all that speed for very high latency, mostly because of the multi-hop reasoning and real-time critique loops. There really is no free lunch.
Moving on to Part 2, Vector Math and Silent Failures.
Here's a crucial takeaway. Even the absolute best agentic RAG system is going to silently fall apart if the foundational math and data ingestion pipelines underneath it fail. It's wild, but something as invisible as a hidden null byte or a decomposed Unicode character can completely wreck your system. Take the letter A, for example. In Unicode, it can be saved as one single precomposed character or a decomposed sequence of a regular A plus an acute accent. To us humans, they look exactly the same, but to an algorithm, they are entirely different byte sequences. This tiny variant silently breaks traditional keyword lookups, like BM25, and injects a ton of non-semantic noise right into your neural tokenizers. So, normalization isn't just some boring formatting step, it's literally a critical point of failure.
And that perfectly sets up this really fascinating concept, the cone effect of anisotropy. When you use transformer-based embedding models, you naturally hope your data is spread out evenly across this vast, beautiful hypersphere. But because of how the self-attention mechanism works, the vectors actually collapse into this narrow, low-dimensional cone. What does that mean for you? It means even totally unrelated concepts are forced to cluster together, which artificially inflates your average cosine similarity to somewhere between 0.4 and 0.8. It's a geometric nightmare that completely breaks the whole idea of using static similarity thresholds across different datasets. So, how do we actually navigate this hyperspace? Well, we compare distance metrics. First, you've got Euclidean distance, which is super sensitive to vector magnitude. Then there's cosine similarity, which purely measures directional alignment. But check out the third option, the dot product. If you apply a mathematical trick during ingestion, specifically normalizing your vectors to a unit length of exactly 1, the magnitude terms completely vanish. This lets you simplify that heavy cosine similarity division directly into a blazing fast dot product operation, which hardware can execute at massive scale. It's a huge performance win.
All right, Part 3. The metadata filtering dilemma. Have you ever wondered why applying a simple metadata filter actually makes an HNSW vector search significantly slower? I mean, it feels completely backwards, right? If you filter down your dataset, you have fewer documents to search, so it should be faster. But in a hierarchical navigatable small world, or HNSW graph, reducing your candidate pool with a filter actually forces the graph to do way more vector comparisons just to avoid getting stuck in dead ends.
It is honestly a brutal trade-off. Think about it. If you naively pre-filter, the database essentially hides the invalid nodes. But because the graph was built on vector similarity without knowing anything about your metadata, this hiding breaks the edges that link valid clusters together. It traps the search algorithm in local minima. On the flip side, if you decide to post-filter, you get to keep that blazing fast vector search speed. But if your filter is highly selective, you risk filtering out literally all the top results, and your user gets an entirely empty result set. Not great.
This brings us to a really cool piece of math, percolation theory. This threshold elegantly explains why missing metadata creates these silent hallucinations of omission. Basically, if the fraction of valid nodes drops below a certain critical threshold, your once beautifully connected graph literally shatters into small, disconnected islands. The greedy search algorithm just can't navigate across those empty gulfs, completely breaking the navigable edges of the small world graph.
But, thankfully, modern specialized databases have actually engineered some amazing solutions to this fragmentation. Qdrant, for instance, builds specialized intra-category links right into the graph itself. Apache Lucene introduced the Acorn-1 algorithm, which selectively expands its exploration beam to 1,024 nodes so it can effectively jump across those filtered gaps without wasting compute on invalid vectors. And if you're dealing with smaller subsets, say under 10,000 rows, engines like libsql bypass the graph entirely. They use common table expressions to perform exact brute force distance calculations over the pre-filtered subset. Problem solved.
Which leads us to part 4, score fusion and re-ranking.
Okay, so once we've successfully traversed the graph and retrieved our candidates from both dense semantic models and sparse keyword models, combining them is incredibly tricky. Why? Because they output totally different score distributions. Relative score fusion tries to handle this by min-max scaling the raw scores into a common range. But reciprocal rank fusion, or RRF, takes a totally different route. RRF completely ignores the raw similarity scores. Instead, it proves way more robust against outliers by simply looking at a document's ordinal rank position in the list.
And that brings us to a very specific, almost magical number, 60. This constant, where k equals 60, is injected directly into the RFR denominator. But why 60? Well, the mathematical difference in relevance between being rank number 1 and number 2 is usually massive. But the difference between rank 50 and 51? Barely noticeable. This constant of 60 dampens that extreme difference at the top, ensuring no single retriever completely dominates the final fused list. It ultimately rewards documents that consistently show up across multiple retrieval strategies.
Finally, part 5, conquering the context window. So, think about where we are. We've normalized our data, navigated the anisotropic geometry, successfully fused our vectors, and bypassed the metadata bottlenecks. Now we have to ascend back to the surface and inject this data into the LLM. There's a huge misconception out there that if a model boasts a 200,000 token context window, you can just fill the whole thing up. Please don't do that. Simply dumping a massive context into a model guarantees failure because of the lost-in-the-middle phenomenon. Thanks to mathematical attention decay and positional encoding, the LLM will heavily prioritize the beginning and the end of your prompt, and it will silently ignore the exact facts buried in the middle that you just worked so hard to retrieve.
This makes setting your retrieval budget, your K-value, a really brutal precision recall trade-off. If you pick a low budget, like 1 or 2, you save tokens, sure. But if the answer is fragmented across multiple documents, you're literally starving the LLM of facts. On the other hand, pick a high budget of 20 or more and you maximize recall, but you end up diluting the high-signal content with noise, which completely overwhelms the model's attention mechanism. Relying on a static K-value is a complete trap.
So how do we actually fix this? Well, the state-of-the-art solution is to completely decouple retrieval from generation. Here's how you do it. First, fetch a really wide net, say 20 to 50 high-recall candidates using a fast-by encoder. Second, pass those chunks through a highly precise cross-encoder re-ranker to find the absolute top 3 to 5 chunks. And finally, at step 3, you can even use a smaller, blazing fast LLM to compress that text, extracting only the most relevant sentences. This pipeline is exactly how you ensure that only high-density, high-signal information ever touches your primary generator's context window.
Which leaves us with a pretty provocative question as we wrap up. As we scale from basic keywords up to these autonomous agentic graphs, are we truly optimizing our retrieval architectures? Or are we just brute forcing the math and crossing our fingers that the LLM figures it all out? As AI systems get more autonomous, it's so tempting to let the LLM just paper over the cracks of bad data pipelines. But mastering enterprise RAG means deeply respecting the underlying geometry of your data, from those tiny Unicode bytes all the way to high-dimensional graph percolation. I really hope this explainer gives you the structural map you need to build with absolute confidence. Thanks for joining me on this deep dive, and keep exploring.